I'm presenting control flow attestation today, and I will also be presenting my recent research work. So I think it will give you an idea also how if you want to pursue research, say in field security, uh, then what kind of problems exist. And I think that it will also help you in the sense that whatever you have learned in the last 3 days, you will see all getting applied now in this problem domain. And so, with that, let me get started with control flow attestation. So, yesterday we were looking at trusted computing, and we discussed in trusted computing that we want to say build trust into a remote party, right? Uh, we want to build trust in a remote party. For in that example, our remote party was a cloud provider, and we were saying that we do not trust the cloud provider. So, is there a way by which, as a client, can I get a surety from this cloud provider that the cloud provider is actually running the correct softwares on the machine where I will be giving my code and data? Because I want to protect the core confidentiality and integrity of my computation, which is happening on this remote machine. So then, with that motivation, we looked at the attestation protocols. In particular, we looked at secure boot attestation, also called trusted boot attestation. And the trusted boot attestation process required a root of trust. And so we said that we do not trust any other software running on this machine, and we can only trust the hardware and such as a trusted hardware. So that trusted hardware comes in different forms, such as a TPM or a SGX or a trust zone. And a TPM stands for Trusted Platform Modules. And then we looked at some details of TPM. What TPM can achieve, like what can you do with a TPM? Followed by that, we said that secure boot attestation is not enough because uh, because the cloud provider in this example can later run a malicious binary on the machine once you have given it your code and data. So there is no way with secure boot attestation to know that what is happening after the secure boot has happened. After the boot process, if the your cloud provider starts a malicious binary, then you as a client would not get to know what is happening there. And so then we talked about trusted execution environments, and we said that we can run our entire process, our entire this process that is basically your client code inside a trusted execution environment, such as provided by a ARM trust zone. And in ARM Trust Zone, we saw that ARM Trust Zone, which is your hardware, that hardware allows your processor to run in two different modes. One is the normal world, one is the secure world. And if you run any of your computations inside the secure world, then those will be protected from any attacks from outside that is in the normal world, and you trust the secure world. So here your assumption is that anything which is inside the secure world is not malicious. And for that assumption to hold true, it is very important that you run minimal amount of code inside that secure world. Because if you are going to put any binary, even like from a third party, then if you run anything inside your secure world, such as say a full-fledged Linux kernel which has memory vulnerabilities, and if you start running that inside your kernel, of course it will be vulnerable to attacks, the kind that we have seen, such as the buffer overflows, format string vulnerabilities, heap exploits, etc. So whatever we are going to run in the secure world has to be minimal. Okay, so it's not like I can take any application and if I run it inside, by running a malicious application inside the secure world, I can tamper with the security of the entire secure world also. So that's why we are still going to run our applications in the normal world. And we're going to use the capabilities of the secure world to ensure that the application in the normal world is running in a secure way. So to make that, so let me just to make that concrete, like what I'm saying, maybe I will, sorry about this. Yeah, I will just go to some slide here and I will just reiterate what I'm saying. I'm saying that this is your secure world, okay? And you want only trusted applications in the trusted OS to run. So if you have an application, let's say you have a WhatsApp application, of course you can run WhatsApp application inside the secure world. But by doing so, so you are going to put only those parts inside, only those applications inside the secure world which are trusted. Okay, so these applications should have, like, say, minimal these applications should have, say, minimal code base. And similarly, your trusted OS is not a full-fledged normal OS like Linux. It's only just a very stripped down version of Linux. Okay, not basically even Linux also. It's just a minimal OS and does not have all of the features such as Linux. So that's the motivation and for running the application still in the normal world. Now, with that, I would stop and see if there is any question. Is there any question from last class? Not just from now, what I said. If you have any question from the last class, then please let me know so that I can clarify that before going forward. Okay, so I assume that there is no question. If you get a question later, then please let me know. And so let me get started. So I will now start with control flow attestation, and I'm going to tell you what is control flow attestation. So control flow attestation basically means that we want to verify the program control flow. Program control flow. Now, why is it important? So we were looking on day 1 and 2, we were looking at these attacks, right? Exploits such as buffer overflow exploits, and the types of buffer overflow exploits were these return to libc or return oriented programming attacks. And then we also looked at the format string vulnerabilities. And these different kind of exploits can be used by an attacker to change the control flow of your program. So the attacker can change the control data such as the return addresses, code pointers, conditional variables which are stored on your stack or the heap region. And then by corrupting the value of these control data, the attacker can modify the control flow path of the program. Basically, it can run some other functions or do some arbitrary operations in your program which were not legitimate, which originally should not have happened. And we had seen example of this in return to libc demo as well. We saw that by changing the return address, we can uh, execute a function in the library in the libc, and even though that function was not originally called from your program. We also looked at return oriented programming, where the attacker tries to find these short sequences of code ending in ret, and then the attacker tries to stitch them together by placing the addresses of these gadgets on the stack, and then it will be able to stitch them together and do some arbitrary operation. Even it can do something which is not already part of your program, and that gives the attacker a lot of power. And it has been shown that ROP attacks are Turing complete, meaning that the attacker can do basically anything it wants to execute. So given the severity of these kind of attacks, and we have also seen that the defenses which we studied, like the WXOR X, ASLR, stack canaries, CFI, and your bound checks, we saw that they're not always effective. So you may need to put maybe a lot of these defenses together to try to prevent these exploits. So when we saw these defenses and we evaluated whether they prevented these kind of an attack, we saw that none of these defenses was able to prevent all of the attack. For example, CFI was not able to prevent the data only attacks. So, and of course, control flow attestation, which we are going to discuss now, I should clarify that it also needs data, needs to check the it also needs to be used in conjunction with a data integrity attestation approach to verify to ensure the integrity of the data. But how is control flow attestation different from control flow integrity? Is the is in the way that control flow integrity is an approach to prevent the attack from happening. Okay, and it is preventing from the attack from happening. But as an end user, if you have say given your code to execute on a remote machine, and even if you have uh, instrumented it with CFI, you how would you know that if there has been attack or not? So it does not give you a proof, it does not generate a proof of what is happening in your program, and that we can achieve with attestation. And particularly we are looking here now control flow attestation. Hopefully it will become now clear more in the next few examples. So I'm going to motivate control flow attestation with this example. Let us consider that there is a patient named Peter, aka the prover in this case. And Peter is using a syringe pump device, such as an insulin pump. Okay. And what does this insulin pump device do? Is that you can give it a command. So if you give this insulin pump a command, say inject 1 ml of medicine, then the insulin pump is supposed to inject 1 ml of insulin inside the Peter's body. Now, since this is also just a normal program and it can be vulnerable to these memory exploits, so it may so happen that maybe you intended to give a command like inject 1 ml of medicine, but the attacker changed the control flow of the program and thereby making it inject say more amount of medicine. Say you said inject 1 ml of medicine, the attacker changed it to change the data value which is stored on the stack, which is saying that the amount is equal to 1, maybe the attacker changed it to 100. And then the attacker has injected, then would be able to make the syringe pump device inject 100 ml of medicine, which can be fatal to the patient. So in this setting, your doctor, let's say, is Victor, and Victor here is the verifier, and and this doctor Victor, let's say, sends a command inject 1 ml of medicine to the Peter's device, which is syringe pump here. And in response to this command, what Peter also wants is a proof of execution. It wants this it wants this device here to give a proof of execution, to send back a response which will be used by Victor to verify whether the command executed correctly or not. Now let's understand it with the help of this control flow graph. So as we had discussed during CFI, that CFI requires a control flow graph of the program. What is a control flow graph of the program? So you compute the control flow graph, which consists of it's just a graph representation of your program. First, you compute it on per procedure level. That is, for each function, you're going to construct this control flow graph where uh, your nodes are the basic block and the edges are the control flow transitions, such as your jumps or Yeah, basically mostly your conditional or unconditional jumps. Okay. After that, you're going to take this per procedure control flow graph, and then you're going to also compute a call graph for your entire program, which where the nodes are the procedures of the or the functions, and the edges are the calling relationships between these functions. And then you are going to merge together both of these graphs to generate the graph control flow graph of your entire program. So let's say that our program that we are looking at right now for this example purpose is a very simple control flow graph which has only these six basic blocks: BB1, BB2, BB3, BB4, BB5, and BB6. And let us say if you give a command input 1 ml of medicine to this control flow graph, then it should execute. So this is the truth value, okay, which is highlighted here, that let's say it executes this path. So it first executes the basic block 1, that is the instructions in this basic block. After the At the end of the basic block, let's say there is a condition like if and else condition, and you can either go to BB3 or BB2. So based on the this input, let's say it goes to BB2. Again, there is a condition here, and then it goes to BB5, and then finally it goes to BB6. So this is your expected path, let's say, for this input. So note that your path in the program will change based on the input. So if you give a input inject 1 ml of medicine, maybe this is the path. If you give a input say inject 2 ml of medicine, then your path might change. So that is a per input, there will be a different path. Okay. Now, as we had discussed yesterday, that in attestation we measure something, okay? And what does measure means? That here we are going to, there we were computing the hash of the, we were computing the hash of the next uh, component in the boot sequence and giving it to the TPM. Here, what are we going to measure? We are going to measure the path in this program. So this program, when given input 1 ml, inject 1 ml medicine, is taking this path. So we are going to measure that what path is being taken by the program. So at runtime, so this is a runtime attestation of this particular program. So note that this is just an application which is running on your machine, and we are attesting this particular application, which is the syringe pump application running. So this is now only for this application. So not for like other components. You're only attesting one particular application on your machine right now. And you're going to measure, you're going to record that what path is being taken by the program. And then once you measure what path was taken by the program, you're going to send back your measurement. You're going to say, okay, this program in response to your command input inject 1 ml of medicine, it executed this control flow path consisting of the basic blocks BB1, BB2, BB5, BB6 in this order. And this is the proof of execution that I am giving you. And of course, this proof of execution, this will be served as a proof of execution only if we have a root of trust, as we were discussing. Like this measurement must be computed by in a secure fashion. So we need to have a root of trust, which is going to generate this control flow path. So after that, let's say for now, assume that you use the trusted hardware, and the trusted hardware is basically taking this measurement. Okay, so the trusted hardware is taking this measurement, and we will see how the trusted hardware will do so. Okay, so the trusted hardware has, let's say, generated this control flow path which was taken by your program at runtime, and it has signed this and sent it back to Victor. So now Victor can basically it can trust that this is coming from the trusted hardware. Now, how will Victor verify that whether this is a correct path which should be executed in response to my command or not? So for that, what Victor does is that he creates a measurement database. What is a measurement database here? The measurement database is just a mapping which is mapping the different commands that your program can take, such as inject 1 ml medicine, inject 2 ml medicine, etc. Whatever, whenever you give a new input command, you're going to put that command here, and then your verifier is going to run the same program in a benign setting. Benign setting means that under control conditions where your program cannot be attacked by an attacker. So it's going to run this program under controlled condition in a benign setting, that let's say in a secure environment, and it is going to construct such a measurement database which is mapping the various commands to the path, uh, to the valid paths in the program. So when this proof is sent back by the device, syringe pump device, here it is going to take this path, incoming path, and it is going to check it against the path which is present in the database, and it will check it, and if the both the paths are matching, then it will output that okay, it is a valid execution, so my command ran correctly. But if both the paths do not match, then doctor will come to know that the command was not run correctly and something else was run. So then the doctor can take action. Also, this is important for audit purpose. So it will give us like we will exactly know that what was happened in the program. And this is just one example that I gave you. There are many areas or many applications where such attestation can be useful. So this is control flow attestation. Control flow because we are attesting the control flow path. So you can also call it control flow path attestation because we are attesting the control flow path of the program. In short, it is called control flow. It is called CFA. Okay. So now before I move forward, do you have a question in the setting of this program problem? So I've allowed mic for you since there is only you are the only one attending right now. If you have a question, then please feel free to unmute yourself and then ask a question at any time. So this is the control flow attestation setting. Okay. Now, this you, I'm sure, would understand very well now based on what we have discussed in the previous 2 days, 3 days, is that runtime attacks are possible on your program. So if this is your program and if you give it inject 1 ml medicine input, then this is your expected path. And then there are many threats which are possible. So the first threat is that, of course, the program binary could be modified. So maybe you have this syringe pump binary, and maybe the attacker just completely changes that binary, replaces it with a malicious syringe pump binary. So then, even if you give it a correct command, if you say inject 1 ml medicine, it will do something else completely. So that is possibly first threat. And maybe I will ask you, can you tell me how will you protect from this? You can think about it. How will this be protected? How will uh, how will you ensure that the correct binary is started? How can you ensure that the correct binary is started? Okay. You can also unmute yourself. And here, how can you ensure that the correct binary is started? So I'm saying that the binary could be replaced with a malicious binary. Okay, syringe pump binary was supposed to execute. The attacker might start some other binary and not the syringe pump program, original syringe pump program. So this we can achieve with secure boot. Okay, because the secure boot process is not up to till OS only. The OS can attest the processes which are started. So the OS can, when it is starting this process, can attest for you that what binary was started. So then it can provide you the hash chain, and that you can use to verify that the correct binary was actually started. Then the second type of attack is code injection in P. So this we had seen during the buffer overflow exploits, that the attacker can inject a new code into the program. In particular, in the demo, we were looking at create shell. So the attacker can try to inject new code in the binary. And for that, we saw that to prevent those kind of attack, we can use W XOR X. So we can make the code pages non-writable and the data page such as stack non-executable. So then the attacker will not be able to inject any new code. The third kind of attack which is possible is the return oriented attacks or the code reuse attacks. So the return oriented programming attacks do not require an attacker to inject any new code into the binary, and so the attacker can still continue to exploit the buffer overflow vulnerabilities to hijack the control flow of the program. So this is something we had looked at that can be prevented, or CFI comes defense is basically for this type of is applicable here. So see, with CFI we can prevent such kind of an attacks with such kind of attack. Then the fourth kind of attack is input corruption or the data corruption. So maybe you Victor sent command 1 ml of medicine, but what input was actually fed to this program? That we do not know. The attacker can try to change the input as well. Maybe it does not change the control flow program, uh, it just changes the data which is stored in your program. So the data only attacks are also like possible. The attacker can try to just change the data of the program. And note that even by changing only the data of the program, when we were looking before, we had discussed that if your program has this auth variable, okay, which is indicating whether the user is authorized or not. If this auth variable is set to 0 on your stack, the attacker can corrupt the value of this auth variable and change it to 1, which will allow the attacker to execute code which only the authorized user should be allowed to, or maybe get access to some data which is confidential and should be only accessible by authorized user. So the input corruption or data corruption attacks are also possible, which can also cause changes in the control flow of the program. Lastly, there can be physical attacks on this machine, and therefore the physical attacks can try to also change, say, the data or the controls of the program. This we have kept here out of scope. Okay, so we are not going to prevent this kind of attack with this CFA mechanism. The CFA mechanism is going to prevent these kind of an attacks. Input for the input corruption or data corruption type of attack, it only prevents those attacks which changes the controls of the program, and not the attacks which are like data only attacks are not prevented. In fact, sorry, I should correct myself that it's not a preventive mechanism, it's actually a detection mechanism. So it does not detect the uh, attacks which do not modify the control flow of the program. Now let's look at these attacks one by one. So the first one is that here the attacker can inject a malicious code such as A in your program, and then it can corrupt the return addresses. So for example, if you were returning back from BB6, then it can return the it can corrupt the return address, and then it will be able to execute the injected malicious code that we saw. Or it can change the return address and then point it to some other location in your program and start executing from there. Or it can change the conditional variable such as say auth variable, and then it can execute, change the direction of this branch. So instead of taking the else branch, the program is going to take the if branch, which is the true branch. So these are just examples like where the exploits can happen, how the exploits will happen. Now, with CFA, what you're going to do is that you're going to record the path. So you're going to record that first BB1 was executed, then BB2 was executed, then BB5, then BB6, and then A will also get recorded. So your CFA is basically a mechanism which is going to record everything, which your program is doing. So how will it record? So similar to CFI, control flow integrity, we are also going to add additional instructions in this program to record this path. And these additional instructions are called instrumentation, as we had seen. So now the problem that we are trying to solve here is to record the program execution path securely. So we want to record whatever is your program doing. So it's like you're going to monitor what your program is doing. Okay, and you need to do it in a secure fashion. What does securely means here? That your recording mechanism, your measurement mechanism should not be cannot be tempered by the attacker. Your attacker can change anything else in your program, such as it can try to corrupt the data which is stored on the stack. It can try to change the input which is given to the program, but it cannot, it should not be able to tamper with the CFA mechanism. Now, how is that possible? We will look at that in detail. Maybe I will just skip this slide, but this slide is basically just showing some works which have happened in this area. C flat is the first work which was actually published. C flat is the first work which stands for control flow attestation only, and this was the first work which was published in 2016 and which proposed this problem. So they were the first one to propose CFA. Then there have been other works. I've only put here 3 works, and the last one, which is BLAST, it's our work, which was published in 2023 CCS conference. Now, what are the assumptions when we are trying to solve this control flow attestation problem? So, as uh, as you have seen earlier, that whenever we are going to try to, whenever you are telling any security defense or an exploit, you have to lay down your assumptions and your threat model. Okay, so here I'm telling you the assumptions that are made usually by these control flow attestation techniques. The first assumption is the presence of a secure hardware. So like we were looking at secure boot attestation, here also we need a root of trust, and that root of trust here is our secure hardware. In particular, we were working with ARM trust zone. And as we have seen, ARM trust zone divides your processor modes into these 2 execution modes. Your processor can either run in the normal world or the secure world. And the switching between these 2 worlds is enabled by the secure monitor. Your secure monitor runs in EL3, execution level 3, which is the most privileged execution level on an ARM processor, and your applications runs in EL0, which is the least privileged execution level, and your trust OSs run in EL1. Now, to differentiate between whether the normal world OS is running or the secure world, your processor has a bit called NS bit, non-secure bit, in a configuration register, and that bit is changed by the secure monitor to indicate which world is running. Now, your monitor is the only software which can change the from normal world to the secure world. Okay, and when it is changing from one world to the secure world, it must store the context of the current world, and it must restore the context of the other world. Okay, so it's like normally when you context switch from one process, from a process, let's say this process is running and you make a system call, you go to the normal world, then first your kernel is going to store the context of this process and then start executing. Now, what does context mean? So the context only means storing the values of the registers and the process state. So this is the context. The context of a process is its state. What does the state consist of? The state consists of like the values in the register. So when this process was executing, it was using definitely some physical registers, like which are mentioned in your binary, and those register had some specific value. Now, if you start executing OS, then you must first store the context of the process and then restore the context of the OS. So that was done here, one context switch. Similarly, there is a context switch when you want to switch from normal world to the secure world. And I also should mention that this normal, when you switch from normal application to the normal OS or trusted application to the OS, basically in general from an application running in user mode to the OS, there is this context switch, and it is usually a costly operation. Similarly, this switching from normal world to the secure world is even a more costly operation. Okay. So let's say if you have to switch from normal application to the trusted application, so it involves switch from application to normal OS, then from normal OS to secure monitor to trusted OS, and then trusted OS to trusted application. So this is a longer process, and then more context are being stored and restored. So it's actually a costly process. So that is about hard trusted hardware here. Then the second assumption is data execution prevention is enabled. What does that mean? It means that in your application, the code pages, if this is your process memory address space, which is divided into code and data, and if your code pages are only read and execute permission, and your data pages have only read and write permission. So you cannot change your code, and you cannot write some arbitrary code in your data region and then try to execute it. So that is data execution prevention, or WXOR X, that we had seen. Then the last assumption that we make for this CFA works, basically these all the CFA works, they are usually these works have been done in embedded systems only. So they have not been done so far in like server class applications. So they have only been done for embedded systems. And in embedded systems, it usually happens that there is only one application which is running, and the application directly runs on the hardware. So there is no OS as such. So there is usually only one application which is running directly on the hardware. And this application is compiled together with minimal interrupt handlers, which it will be using to communicate with the devices. Okay, such as in an embedded device, actually there will be like sensors, or say analog digital converter, etc. So this is your embedded. Consider this like a embedded system, embedded setting, where only one application is running, and that application is running directly on the hardware, and there is no privileged software like OS here. So this is such setting is called a bare metal setting, where there is no OS and your application is running directly on the hardware. It's also called a bare metal. So these are the three key assumptions that we have in CFA. And now, next, let me define the threat model. So in the threat model, we define that what parts of your system are trusted, and where your adversary can be present, and what power your adversary has. So you trust only the secure world, or the secure monitor, which is part. So this entire thing is part of your secure world, and you trust only the secure world. The normal world is not trusted, and there is only one application running here, which is the normal application. And since there is no OS in this setting, this normal application is going to run in EL1. So your application is actually running in EL1. It is compiled with the minimal functionalities it need to talk to the hardware, such as interrupt handlers. So, and your attacker can have access to this application. So your attacker can corrupt only this application, but it cannot corrupt any other part, like the secure world, applications in secure world OS, or the secure monitor. So that's the assumption we have with respect to the threat model, and this is where your attacker is. Now, what are the capabilities of the attacker here? The attacker have capabilities such as the attacker can try to change the control flow of the program by giving it a malicious input to the binary, and therefore can try to say do buffer overflow attacks, or it can try to do a format string vulnerability attack and so on, heap exploits, etc. So that's the attacker can try to do in order to change the control flow of the program, and that is what we are trying to detect here. So this is a detection mechanism. Now let me stop and ask if you have any questions with respect to the problem setting and assumptions that we have laid down, and also the threat model. Is there any question? Okay, so if there is no question, let us see how we can solve this problem in a strawman approach. So here, this is a control flow graph of your syringe pump program that you want to attest. And this program will actually be running in this application here, normal application. So this is your syringe pump application now. And this application is running in the REE. REE is rich execution environment, which is another name for normal world. So it's running in the normal world, and this is this side is the trusted execution environment, let's say. And the trusted execution environment provides secure storage. As we were seeing yesterday, that the trusted execute that your processor can give this ns bit value to even the devices which are present on your machine, and also to the other components on the chip such as the ram and other like modem caches, etc. So then the entire processor and also the other components beyond the processors are divided into the has this knowledge of the word in which the processor is executing, and that provides the isolation between the data which is being stored on the same memory or storage. So that's how your ARM trust zone is able to provide a secure storage which cannot be accessed by the rich execution environment or the normal world. Okay. And then let's say you give an input to this program and you want to record the path which is being taken by this program. Then what will happen is then when this input is when you execute this basic block one, and then at the end of this basic block one, let's say you take the false branch. So if you take the false branch, then it is going to we are going to instrument this program. We are going to add now here a new instruction on this program. That instruction, as we were talking yesterday, will be a SMC instruction. What is your SMC instruction going to do? It is going to switch from the normal world to the secure world. So assumption here is that W XOR X is enabled, which allows the attacker, which does not allow an attacker to change the program binary. So the program binary cannot be changed, and therefore this SMC instruction cannot be removed from the program. So your program will have to execute this SMC instruction which is present here. So when this basic block one is executed, and if the program takes the false branch, then assume that so imagine that there is this SMC instruction on this edge, and this instruction will get executed and you will be switched to DEE. And when this instruction is executing, you are passing to this instruction the ID of the basic block one. So you can pass some arguments to the secure world from the normal world by setting the arguments to this SMC instruction. So let's say you have set the argument to the SMC instruction as BB1. Okay, so that also is like a hard-coded value which is present in your code, and that cannot also be tampered with by the attacker. So this instruction will be executed with the ID baby1, the ID of this basic block. Okay, so and Then when you switch to the TEE is going to record that value. So maybe it is going to invoke an application, trusted application in the secure world, and that trusted application is going to take the argument, and that is the BB1 basic block ID, and it is going to store that in the secure storage. Similarly, when basic block 2 is executed, and let's say the false branch is taken, so just to clarify, this SMC instruction is actually present on all the edges here. Okay, imagine it is present on all the edges. So whenever you are going to take any edge, it will lead to a SMC instruction getting executed. So that is going to make the program switch from one. So that is going to make your processor switch from the normal world to the secure world, and you're passing the basic block IDs as the argument to the SMC instruction. So then there'll be a switch, and the switch is going to record the BB2 ID here. Similarly, your BB5 will execute, followed by the edge, and then this you will record BB5 in secure storage. And when then BB6 is executed, you will record here BB6. So this is with this mechanism, if any other path is recorded by the program, that will also get recorded. So if your program takes BB1, BB2, and BB4, BB6, then there will be SMC instructions here which will cause it to switch, and then the values which will be stored here will be for that path. Because on every edge you are making a SMC switch, you are making basically a switch to the trusted world, and you're passing as argument the ID of the basic blocks. So this is how you will be able to record what path is being taken by the program. Okay, and here what are the trust assumption is that the program binary cannot be changed. So the program binary cannot be changed to remove this SMC switches, basically SMC instructions, and therefore the world switches. And another assumption is that your trusted hardware provides this separation between the rich execution environment and the trusted execution environment. And it is providing a secure storage where these values will be securely stored. And your attacker cannot change these values once they have been stored. Now, if we map it back to our setting, which we looked on the first slide, then this program is the syringe pump program, which is running on Peter's device. And Victor, who is the doctor here, is going to receive a signed path commitment from the trusted execution environment, from the trusted hardware. The trusted hardware is going to take these values along with the signature over these lines. Wait a second. Yes. Okay, I'm very sorry about that. So let's continue from where we stopped. So here we were looking at that the path commitments are going to be then sent to the to Victor along with the signature over these path commitments, and then Victor is going to take these values and verify them against the values stored in the measurement, and Victor will verify that whether the path is the actual path or not, it's a correct path or not. And if the path is different from what is stored in the database, then Victor will be able to detect a violation. So this is how you would record, how you will, this is basically entire process for control flow attestation. And with this, you are attesting the control flow path of the program. And so this is the setting. And if you have any question, then please let me know. Okay. So this approach, which we just discussed, this approach for control flow attestation was proposed by this work, C flat, control flow attestation and embedded system software. And what we did in our work that we took this approach, work, we took this approach and then we evaluated on a benchmark of embedded program. So mbench IoT benchmarks is a suite of embedded real-world embedded programs, and we took this benchmark and evaluated these approaches, C flat and OAT. So OAT is also another approach, attestation. This was proposed in 2020. So we took these approaches and then we evaluated them on mbench IoT benchmarks. So we recorded the total number of T domains which is encountered at runtime. So for that, these are the T domain switches. These blue lines which are crossing the boundaries are the domain switches. And I'll be referring to this term again and again in this presentation. Blue arrows which are going from the RE are called domain switches. So we recorded the total T domain switches encountered at runtime. Note that in this example, there is a TEE switch at every basic block. Okay, there's a TEE switch at every basic block, and that is what we are recording. That what how many? So if for this particular example here, which I'm showing on the slides, there are only 4 T domain switches. So these are the mbench IoT benchmark programs, and these are the total D domain switches encountered at runtime. And for C flat, as you can see, for this program, Mont 64, it encountered around uh, 857 million T domain switches. Okay, OAT paper actually improved upon this and it was able to bring down the number of T domain switches to 392 million domain switches. So as you can see that these are very large values. So let us now see, take one of these values for Nettle SHA-256 benchmark and see how T domain switches are encountered at runtime going to impact the performance of the program. So the effect of T domain switches on the runtime of the program, to see that, consider this program Nettle SHA-256 for which C flat incurred 223 million domain switches and OAT incurred 34 million domain switches approximately. So if this, so when we evaluated these benchmarks, we found that on Raspberry Pi 3, which was the evaluation platform for our studies, we found that this program took only 12 seconds to execute on Raspberry Pi 3. And note that, as I was saying in the beginning, the T domain switches are a costly operation and can take up to 190 microseconds on a Raspberry Pi. So one TE domain switch take roughly 190 microseconds. So if there are only 100 T domain switches, it may not affect the runtime of your program. And if there are 1,000 even, it won't affect the runtime. Like basically the runtime will not exceed a lot. So that would not be visible. You won't be able to have a visible, if you probably won't have a visible effect. However, when the T domain switches are like in millions, at that time, if you run such a program with the C flat approach, then you would find that if this is the number of T domain switches encountered at runtime and you multiply it with the cost of one TE domain switch, which is 190 microseconds, it runs in more than 11 hours. So a program which was originally running in only 12 seconds now run in more than 11 hours. Similarly, for OAT, a program which was originally which is basically taking 34,000 million domain switches, when multiplied with 190 microsecond, give roughly 2 hours. So the program, instead of 12 seconds, ran in 2 hours. So as you can see, these are very high overheads. So there is something like performance overhead is also a very important criteria when we are talking about the security approaches. Because if your security approach, so far in this workshop, we only were focusing on the defenses and talking about whether they prevent some attack or not. But why is say ASLR so widely deployed even though it doesn't prevent the attack all the time is because it does not cost anything. It is only randomizing your address space. So it's very important when we're talking about security approaches to also evaluate the performance overhead. If your security approach is going to make your program too slow, then that is never going to be implemented in real world. So these approaches, although they have proposed a very good attestation mechanism, they incur very high overheads. Okay, and they impose over 1,000 time and 5,000 time overhead respectively on not just this particular benchmark in this suite, in fact on all the benchmarks. And the reason for this is the high number of T domain switches. And in fact, in these papers, if you are interested in reading about this area, and let's say if you start reading C flat note paper, then you will say that I told you in the presentation that incurring such high overheads. But in fact, in the paper, if you go and study, you will find that C flat reported 0.13% overhead for the syringe pump benchmark, and OAT reported an average overhead of 2.7% only on 5 embedded program. So they have reported very low overheads, while I'm saying they are incurring very high overheads. Now, what's the reason for low overheads reports in the papers? It's because these works evaluated their approaches only on very small embedded programs. And these small embedded programs were like had only few hundred of control flow and events at runtime. So at runtime, these programs encountered only say 100 control 100 T domain switch, and 100 T domain switches will not cost anything, because 100 times 190 microseconds would be just like 19 milliseconds, not, yeah, 19 milliseconds. So that is not going to cost much. Okay, that will not be visible as a overhead. The another thing that they did to even reduce the overhead was that they tested only critical sections of the program. So they took they said, okay, only this function in this program is critical, like only this function is important, and so we are going to attest only this particular part of the program. And that's why they did not attest the entire program, and they were able to even reduce the overheads further. But as it has been shown in other works, such as this probability prediction based mutable control flow attestation scheme, as it has been shown in other works, that if you do not attest the entire execution of the program, then the attacker will be able to still change the control flow of the program and without getting detected. So here our goal is to detect the control flow hijacking attack. So it's saying that if you attest only some parts of the program and not all of the program, then the attacker can uh, still do a control flow hijacking attack without getting detected. And then it is not longer a secure approach. So, in conclusion, the prior control flow attestation approaches that we have uh, that we just looked at, one of them is C flat. These prior control flow attestation approaches, and that we also studied in our work, they were extremely slow and they attested only some part of the program. So they were not providing us full security, and they were slow also. So that's why in our work, which is BLAST, whole program control flow attestation, path attestation, we propose a attestation approach which is fast and it is more practical. And we even do the attestation of the entire program and not just critical sections of the program. So the key contributions of our work are these three. The first one is that we as we noted in our study that the main reason for high overheads were the large number of T domain switches. So we reduced the T domain switches by local logging. Okay, what is local logging? I'll come to that in a bit. But we reduce the T domain switches. Second, we also note in our work that the path measurement strategy used by the prior work was not optimal. For example, in the approach that we saw, if we record, we are recording every basic block ID. So we're recording the execution of at every basic block. And that, as I will show, that is not optimal because then we have to make a switch at every basic block. Okay, and that is causing this high overhead, that is causing this high number of T domain switches. The third is that we have a more compact attestation report than the prior works, and that we achieved with the help of WPPs, whole program paths. But I will be focusing only on the first and second and not the third because that would be like too much details. And even for the first and the second, I will present only high level ideas. And if you are interested and if you want to know more details, then please feel free to refer the paper. Now, the first part is reducing the T domain switches by local logging. So what is local logging? So we buffer the measurements in a local log, which you are going to allocate in your process, inside your process. So what we are saying, okay, this if this is the address space of that syringe pump program that we are attesting, and if this is the control flow program, control flow graph of the program, this address space will have the code pages which are represented here with the this orange color, and it will have some data region also, which is the green region. What we are going to do is that we are going to allocate a fixed memory region in this data region, and this will be always started at the fixed location only. Okay, so it's a predefined memory region, and we are going to call it a log, CFA log basically. And now, instead of recording the values in the secure storage directly, we are going to buffer these values in this log. So now, instead of going there and storing them, we are going to record them here. So note that this control flow graph is for this program code, which is written here. So basically, your code itself is recording these values in this log here, right? And when this log becomes full, then we are going to switch to the TEE and store these values in the secure storage. So note that earlier you would have to make 4 T domain switches to store these 4 values. Now you have reduced that to only 1 T domain switches. So there is a large reduction in the number of T domain switches that we have to do now in order to store these values. So in our work, we have actually allocated 1 MB log region, so it can store these basic block. So if we do say only record the basic block IDs in it, so it can store a large number of basic block IDs before we will have to make a switch to the TEE. So this is buffering, and with this buffering approach, we have been able to reduce the number of T domain switches. But you will then know, but as you know from our discussions, that this data region is actually accessible by this code. So the code can try to corrupt the values that you are writing here. Now, how do we prevent the code from tampering with the values which are being stored here? For that, we are going to use another approach, but let me first tell the problem again with the help of this example that the corruption of log data is possible. So let's say your code has this store instruction, which is storing some value at some address. Now your attacker can change this address and point it inside the log. Now, if the attacker is able to change the address and point it inside the log, then attacker can basically write anything. It can overwrite the entire log with values of its own choosing. So it will be able to change the control flow of the program also, and it is then going to change the log also, and the attack will remain undetected. And therefore, the final values which will be stored in the TE will also be corrupted. So the TE is storing taking these values from here only, from the log region. Since the log is corrupted, it will also get corrupted. So to protect the integrity of this log data, which is of this log, which is part of your process address space, we use a technique which is called software fault isolation. And I did not discuss this during the classes, but what software fault isolation does is this that it is going to take that whenever there is a store or load instructions, then in our case here we are only concerned with store because we want to protect the integrity. But if you also want to protect the confidentiality, then you do the same for the load instructions as well. So for the store instructions, before this store instruction, we are going to add additional instructions in the program. These additional instructions will be added by the compiler. And I'm just reiterating that since the program code is non-writable, these instruction cannot be removed by the attacker. So before every store instruction, we are going to add a check. And the check will be something like it is going to take this address of store instruction and it is going to check, is this address inside the log region? And if this address is not inside the log region, then it will let the store instruction execute. However, if this address is inside the store instruction, then it will abort the process. How? So it's like here you will have the SFI check which is placed before the store instruction. Okay, so you have a store instruction. Before that, there is a SFI check. And so this is just doing a comparison here using this address and is comparing this address along against the log start address here, or basically the base and bound of this log. So it's going to take this address and check whether this address is lying within the bounds of this log or not. If it's not lying inside the log, it's going to allow it to happen. And if it is lying inside this, then there'll be instruction here which is going to abort the process. So if the comparison is true, if this is inside, then this will be instruction will be here, which is going to abort the process. Because we have detected that the address is trying to write into the log and it's not a permitted operation. Now you would think then how can the code record the values inside this if we are going to like I was earlier saying the code is going to write in this log and record the values. So we have these we are making a distinction between store instructions. So there are store instructions which are originally part of the program, and then there are these store instructions that we have added to record the values. So the store instructions that we add as part of our instrumentation, there will be no check before those store instructions, and they will be able to write to the log. But any other store instruction in the program is going to be checked, whether it's writing inside the log or outside. If it's writing inside the log, the process will be aborted. So with this, we are able to reduce the number of times we have to switch from the normal world to the secure world. Now let me stop and ask if there is a question. Okay. So if there is no question, then yeah. So if there is no question, then let me continue with the next part, which is the optimal path measurement instrumentation using Walrus path profiling. So, so what we discussed till so far is that whenever we are going to record our path measurements now in this local log in the process address space, and if this log become full, then we are going to switch to the TEE, and then we are going to flush this log. Basically, let's say take a hash of this log, and then we are going to record it there. So this is what we discussed. Now, if this log region becomes full faster and faster, like if you are going to record every basic block ID in this log, then this will become full faster, and then you will have to still switch to the TE more number of times. So that's why in order to reduce the number of times that you're writing to the log, that number of basically to reduce the number of log entries, we propose to use another instrumentation strategy. This instrumentation strategy is inspired from the path profiling work, efficient path profiling, which was proposed by Ball and Loris, and this was published in 1996. So we are using a path profiling approach called Ball-Loris path profiling for our instrumentation strategy. And this approach has been shown in the literature to be more efficient than the approaches which have been used in the previous works. And in this work, so this path profiling work, basically what do? They also record the path which is taken by the program, and that is for profiling purposes, such as say you want to find out which path is taken the most number of times, so like heavy paths basically, so that you can then go and do optimizations on those paths. So your compiler is going to say do the path profiling of your program, and then the heavier paths will be they'll be optimized. So this is like not related to security so much, but it is a path profiling. This works are related to like also they also do the same thing, that record the path which is taken by the program. And we are reusing this idea from the path profiling literature here. So what we are going to do is that we are going to compute the path number. Okay, so to compute the path number, we take a register R and we initialize it to 0. Okay, and the register R value is initially set to 0 in the beginning of a function. So note that these path values will be computed per procedure. Okay, and this register in our work, we call it the Ball-Loris register because it's a Ball-Loris path profiling algorithm. Now, after that, we add some additional instructions on some edges, which are the instrumentations. Okay, and these are the Ball-Loris instrumentations. So when your path is going to execute, then it might encounter some of these Ball-Loris instrumentation, which is going to change the value of this register R. So your register R here is the path ID. It is going to compute the path number of the program it is going to compute the path number, like which path is being taken by the program. So then initially it is set to 0, and when your program then starts executing, and at the end of the basic block 1, let's say your program takes this side of, so basically let's say this path is being taken by your program. So you will go to BB2, then you go to BB5, then you go to BB6. So initially your path value was 0. At the end also the path value in R is 0 only. So you're going to record the path value 0. Now this single integer value actually, according to your instrumentations, um, it's going to indicate that the path which is executed is BB1, BB2, BB5, BB6. So like imagine like a table which you have, and the table would have this mapping that if the path ID value is 0, then the path which is executed is BB1, BB2, BB5, BB6. So if you send this value 0 to your verifier, then the verifier would look at this value 0 and would know that this path was executed. You don't need to send all the basic block IDs. You just need, if you send only this value 0, that itself, that's like a path ID. So it's the ID of this path BB1, BB2, BB5, BB6. Next, when this path has been recorded, we are going to switch the TEE, pass this the values of the log. It is going to store them in the secure storage, or it will then sign these value and send it back to the verifier. Now, if another path is taken by the program, let's say if your program takes another path BB1, BB3, BB6, then this instrumentation would have been encountered. So your value of R would be incremented to 1. So then at the end, when you exit from BB6, your value would have been 1. And then you would have recorded here 1. So then value 1 would indicate that path BB1, BB3, BB6 was executed. Okay, so this is how we are going to record what path was executed by the program. So earlier we were recording the ID of every basic block, and that is how we were measuring the path. But here we are using Ball-Loras path profiling algorithm. The Ball-Loras path profiling algorithm says that if your procedure has so for a acyclic control flow graph, if that control flow graph has total of n paths, then it is going to generate a path ID for a unique path ID for every acyclic path, and that ID will lie in the range 0 to n minus 1. So if there are n acyclic paths, then it is going to generate ID in the range 0 to n minus 1 for every path. And this Ball-Loras path profiling algorithm works even for cyclic paths. But for more details, you can refer either to the paper or the Ball-Loras path profiling. Refer either to our paper or the path profiling paper itself. Now, this Ball-Loras path profiling algorithm is effective, and again, it's more effective against the C-flat and OAT approaches like the prior works, and it's more effective in terms of reducing the number of log entries. So as is shown by this graph here, if so compared to C flat, BLAST has reduced the log entries by up to 7 times. So this Ball-Loras path profiling algorithm will reduce the log entries by as much as 7 times. For another benchmark, prime count, it reduces the number of log entries as much as 3 times, and so on. In some cases, it performs worse than, say, OAT, and the reasons you can again refer to the paper for more for that detail. So our experimental setup was consisted of Raspberry Pi. So we were running our experiments on Raspberry Pi, and we were instrumenting the original program by with a compiler pass. So we had written a compiler pass, LLVM compiler pass, uh, to instrument the program. Instrumentation means to add these new instructions into the program. We did it by the compiler pass. So we assume that the program source code is available. Although even if the program source code is not available, you can write a binary rewriter to change the binary. And then this changed binary that we have here will be run on the Raspberry Pi platform. And we evaluated the performance on the MBench IoT benchmarks. So when we compared our C blast approach overhead with the C flat and OAT approaches, so we did it And let's say this is the graph that you have, and on the y-axis you have the overhead in percentage imposed by the approach, and on the x-axis you have the benchmarks. So as you can see here, C flat incurs more than like approximate more than here, it's like 1 million percentage overhead. And oat here incurs more than 5 lakh overhead. Okay. So it's like 5 lakh percentage overhead. While for blast, the green bars are not visible here, and it is so because the blast overhead is very low compared to C flat and oat. It's not negligible, it's not zero, but it's just very less compared to C flat and oat. And sorry, yeah, I skipped a slide. So if we look, if we zoom on blast performance and if we compare it with the baseline performance, then we will see that the execution, if this y-axis is the execution time of the program and these are the benchmarks, then on average blast incurs 67% overhead, which means that if your program was originally running in say 1 second, now it is going to run in less than 2 seconds on average. Okay, so that is the overhead of our approach, which we implemented with by making these two changes. First, we changed the instrumentation strategy and used the Paul-Lawrence path profiling algorithm. And second, we reduced the number of D domain switches encountered at runtime by the program, and we did that by local logging. So, and this figure here shows the runtime overhead breakdown of our approach. So as you approach has used to protect the integrity of the log, the Ball-Loris instrumentation, which is used to record the path values, and the log hashing, which is used to record the measurements from this local log to the TEE. We have break down the runtime overheads into these three parts, and as we can see, the majority of the overhead is due to the Ball-Loris path profiling algorithm. Next, we started this discussion with the syringe pump benchmark, and so we also evaluated our work and compared it against C flat, which also evaluated their work on syringe pump benchmark. So for the syringe pump benchmark, we gave this program different amounts of medicine, like different amount of medicine, which is here bolus, like 0.5 ml, 1 ml, 2 ml. And with our work, last the overheads were 10%, 5%, and 3% for these amounts. While with C flat on this particular binary, it was around 93% for all of these bolus amounts. And these are actually the overheads reported in their own paper. We did not do this study. Like we did not compute these values. These were as reported by them. So in conclusion, what I presented to you today is control flow attestation. And we saw that with control flow attestation, we can build trust in the integrity of the program, which is executing on a remote device. So if your program is executing on a remote device, then with control flow attestation, you can build trust into the execution of this program. You can get a proof of execution of this program that and can know exactly what your program is doing on the other side. And then we discussed one like a very simple way to do it, that by recording the basic block IDs in the trusted hardware, in the secure storage provided by trusted hardware. And but we noted that this will lead to lot high overhead. So then we discussed some approach to reduce the overhead, and that is called blast. And in blast, we reduce the overhead using Walrus path profiling algorithm and reducing the T domain switches by locally recording these values. So this is what we discussed. Now, as future works in this direction, like control flow attestation, these are the future works that can be considered. Like first, uh, we can build robust and practical implementations of these approaches because currently these are only research prototypes, and we can, and they do not support, say, the libraries. So the libraries are not instrumented, they have not been tested for multi-threaded programs, etc. So that can be done. Second, as you may have noticed, then that we made this assumption that the setting is in we made assumption that the program is running on bare metal, so there is no operating system. So when there is an operating system, so then the CFA mechanism that we discussed in this so they will not be secure. And you can think about it, that why would they not be secure in the presence of an untrusted OS? Okay, so there will then our threat model will be changed, our assumptions will be changed, and therefore new attacks are possible, and therefore we need some new defenses. And then the next one is that sometimes it is possible that there is no secure hardware on the device for which you are doing the attest on the device where your program is running. But the secure hardware not on the device, basically your device can have, say, multiple chips. And it may so happen that on the chip where your program is running does not have a secure hardware, but it can be present on the other chip. So how can you use the secured hardware which is present on the other chip to do the attestation is also an area of research. And lastly, when you get this report, attestation report, and you can of course verify it and check whether the program ran correctly or not, but can you also use it to fix the bugs or detect the bugs? So those are the future direction. And now I'll stop and take any questions if there are any. Please let me know if you have any questions. Okay. Okay. So with this, we so far in this workshop, I hope it was useful to you, and we have discussed the memory exploits. We discussed the defenses for those memory exploits, followed by a discussion on trusted computing, trusted execution environment, trusted hardware, attestation protocols. And although that is not the entire, like it doesn't finish here, you can, there are so many more in system security that you can read about. And so then I can recommend you that if you're interested in learning more about system security, then please go and take a look at the courses offered by Professor Vinod Ganpati from CSA department in IISc Bangalore. And if you will Google his name, then you will find out his lectures on YouTube and which are freely available. Also, I highly recommend you to take course from Professor Chester Ribeiro from IIT Madras. So he has a course on secure computers, secure engineering, and that is there on NPTEL. And this is also, of course, NPTEL is a free platform, so you can go and take that course as well. Both of those courses cover a variety of topics, and combined together, I think they are going to serve as a very good combination and would provide you a holistic understanding of this entire security area, system security area. And I should also acknowledge it again that the most of the content that I have presented during these these last 4 5 days is actually taken from these two courses only, and I have learned from them, and it will be really good for you if you are interested in system security to go and check these courses and learn from these courses directly. But if you have any question related to the content of what we have discussed so far, and if you want to discuss more, then feel free to send me an email or leave your questions on the chat box, and I'll be happy to answer any questions. Uh, so, is there any question? Thank you so much for thank you so much for your message. I really hope that this was helpful for you in some manner, and it will help you in the future as well. Yes, I will try to inform everybody about if I organize another workshop like this in the future, and hopefully, I will try to uh, do a more in-depth workshop next time, and like maybe dedicated to only say trust zone or something like this. And I will share the feedback form with you. Thank you so much for your kind words, and thank you so much for joining uh, the workshop and making it a success. Thank you everyone who joined the workshop, and with that, I am going to now stop recording. Yes. Thank you so much for joining today. Bye. I will put all the recordings on YouTube, and I will share the links via the email and also the link to the feedback form. Thank you. Bye.